So this is a quick intro to the continuous uniform distribution, and really they don't come more basic than this when we're talking about continuous distributions, because basically it means equal probability. What's written here is an example of one where it's continuous or practical. If we had a number which was rounded to 70 to the nearest 10, then when it's rounded, remember we're talking about continuous numbers here. When it's rounded, it's going between, it can be, the most it can be is 75 and the least it can be is 65. So that makes it equal to 70. That basically means the number can be anything in between these with equal probability. We're not any more likely, as you might do with a normal distribution, to be kind of centered around the middle. Randomly, they're going to occur with equal probability anywhere along between 75 and 65. Now, if we had the PDF of this particular example, we would just say that fx is equal to 1/10, and that is for x between 65 and 75, and 0 otherwise. And that will describe the probability, and it will be basically the graph of it. We'd have 1/10 here, and 65, 75. Notice the 1/10 has got to be here so that the area of this equals 1. So that's an example, a practical example of the continuous uniform distribution, one which you can see where there's actually some kind of relevance to kind of data that we might come across in the real world out there. So looking at the second part of this question, what is the probability that the number is greater than 71? Now, I'm sure you don't really need to know a lot about probability distributions and continuous random variables to do this. You probably intuitively can see that that number is 4 out of 10 because it could be between 71 and 75. So greater than 71 means greater than 71 exactly. So that's any number between 71. Basically what we're saying is it can be any number greater than 71 but less than or equal to 75. Now I get into some conversations here about whether we're allowed a strict inequality here or not. I'll take it off, or not a non-strict inequality. I'll take it off. But actually, when we look at continuous distribution, it really doesn't make any difference because we're looking at areas, we're looking at ranges of values here. The probability of taking it bang on a number is actually 0. So, you know, we really shouldn't be too concerned about the inequality here. But I do come across people worrying and saying, well, if it was 75 exactly, then it would go to 80. Let's not be too concerned with that. Okay, we're going to change it back to that now. Okay, so we're not really bothered. That's the answer. We can see that would be 4 out of 10. Now, looking at it from the kind of area under PDF point of view, we can see that area is 0.4, just like we have seen. So there's a tie with all the PDFs, all the work on PDFs, probability distributions that we've already seen. It really is as simple as that. Right, so let's look more generally at this. So the general uniform continuous uniform distribution. Uniform distribution. It's very important, the word continuous. There is a uniform discrete one, which again involves equal probabilities, which we've seen in S1. So here we go. We've got A and B. Let's just make A and B, the B being the maximum it could be, A being the minimum it could be, and we should be able to see from this that because the area here has got to be equal to 1, that this number should be 1 over B minus A, because we need it to be equal to 1 over B minus A. This length here is B minus A, so B times by B minus A equals 1. Okay, so that bit means that, and that's constant, the value of fx doesn't change. So that should get us our probability function reasonably okay. We can just say fx is 1 over b minus a with, let's rub off this now, I think you've got the idea. So x being greater than or equal to a and less than or equal to b. Again, I'm really not concerned about the strictness or non-strictness of those inequalities, and 0 otherwise. Okay, so that's our continuous uniform distribution, the fx for it, the PDF. The CDF, really, do we really need the CDF? But the graph of it, if you think about how, because it's going up constantly, the graph of it would have to start at its lowest value, which is A, and finish at its highest value, which is B. And remember, CDF shows a cumulative probability here. It would need to go from 0 to 1. We could use this to get our CDF rather than in the textbook, in the S2 textbook, they actually use integration with limits on it. But this is quite a nice alternative to gain the PDF of fx, because we can just find the gradient. We can see the gradient of this is equal to, it's going to be equal to this length here, which is 1, divided by this length, which is b minus a. Okay, so we can use this to work out the equation of it, because fx must be equal to the gradient. If we're using y minus y1x, we're effectively using y minus y1f mx minus x1. So 1 over the y is equal to the gradient. This is my y minus y1 because it's starting at 0. Basically what we've got, let's start this again, perhaps rushing it a bit too much. We've got a point here which is a0. Okay, so and we've got a gradient here which is 1b minus a. Let's talk in terms of the y of it. So we've got y minus 0 is equal to m, which is 1 over b minus a, x minus a. Okay, so we can see that that gives us y equals 1 over b minus a, or let's write it all as one single fraction, x minus a over b minus a. So that gives us our CDF. It's not used very often, to be honest, but you never know you never know. So as we know with CDFs, they go from 0 to 1. And the thing I just rubbed out, not particularly helpfully, it's x minus a over b minus a. And it's 0 if x is less than a, and that if x is between a and b, and 1 if x is greater than b. So there we go, that's the CDF for it. Okay, there is a proof using integration rather than the graph. I quite like the graph thing that we've just done, method of doing it. Okay, so there we go, we've got CDF for it. Before we go, talk about the mean and variance. Let's go back to the PDF of it again now, draw the PDF back up. Okay. Now, it's pretty obvious that the mean, because of bisymmetry, is going to be here, halfway between the two. So the mean, Ex, or mean, mu, same thing, is like the average of these two. Okay, now that's the average of these two, so that's b plus a over 2. Right, now the variance, Variance, I'm going to have to show this in a separate video because it does involve a bit more work. It's going to take probably as long as it's taken me to do this now. The variance of x, these are given in the Edexcel formulae, by the way, is equal to this. Okay, so that's a continuous uniform distribution. That's all it is. We've seen an example of it. So in the next video, what we're going to do is see a proof of this variance, which is just a little bit of algebra really. The proof is slightly different, that I'm going to do is slightly different to the one in the textbook, so I'm sure you'll all look forward to that. Okay, that's it.